Before I started learning Julia, I had never heard of a graph. What I thought was a graph turned out to be a plot. It was like being unplugged from the Matrix. My entire life up to that point had been a lie. It turns out that a graph is something very different, and something very useful. So, what exactly is a graph?
Hmm.
Well, let's find out. Welcome to Doka.jl, where I explore the vast Julia wilderness and turn my discoveries into wholesome Julia tutorials. Graph theory can trace its roots back to 1736, when the Swiss mathematician Leonhard Euler tackled the now famous problem of the seven bridges of Königsberg. The city has changed hands several times throughout the past centuries, but today the city is known as Kaliningrad, Russia, and the river that runs through the city is known as the Pregolya River. The city has a very interesting history that, unfortunately, we won't have time to get into. But back in 1736, the city was known as Königsberg. It was part of the Kingdom of Prussia, and the river was known as the Pregel River. In Euler's day, the city of Königsberg had two large islands in the middle of the Pregel River, and the islands were connected to each other and to the main banks of the city by seven bridges. So Euler was contemplating this riddle. How can you cross all seven bridges once and only once?
One eternity later.
It turns out that this is a trick question. The answer is you can't cross all seven bridges once and only once. It's easy to cross 6 of the 7 bridges, but no matter which path you take, you'll always be stuck at some point in the city where you'll be forced to cross one of those bridges twice. If you had to describe this situation mathematically, how would you do it? Back in 1736, the language of mathematics had not developed to a point where anyone could explain this situation mathematically. By tackling this problem, Euler became the first to prove mathematically that this problem has no solution. In his proof, he abstracted away the physical map of the city, leaving behind only the land masses and the bridges connecting them. By doing so, Euler laid the foundation for graph theory. Today, we would refer to the land masses as vertices, or nodes, and we would refer to the connecting bridges as edges. The mathematical structure showing the relationship between nodes and edges is called a graph. Graph theory has many practical applications in physical, biological, social, and information systems. Within Julia Land, the graphs.jl package is the gateway to entering the world of graph theory. Graphs.jl was originally called lightgraphs.jl. Lightgraphs.jl was created by Seth Bromberger, who wanted to create a fast and lightweight graphs package in Julia. At some point, James Fairbanks joined the development efforts to become the other core developer of lightgraphs.jl. He would eventually be joined by Mathieu Besançon and Simone Schöly. I apologize for my pronunciations. Originally, there was a different Julia package named graphs.jl, which has since been archived. So at some point, the lightgraphs.jl package changed their name to graphs.jl.
Side eye. Side eye!
This sounds like a juicy bit of Julia lore that I would ordinarily be interested in pursuing, but we have a lot of material to cover today, so I'll leave this story for another time. With that said, Let's jump straight into VS Code and get started. In VS Code, create a new project folder for this tutorial. I'm going to call my folder Tutorial 08x08, but feel free to name it whatever you like. Start a new Julia session by using Alt-J, then Alt-O. Change the present working directory to your project folder. Enter the package manager, and then activate your project folder. Now add the following packages: graphs, simple weighted graphs, graph recipes, and plots. After the packages have loaded, exit the package manager by hitting backspace. Okay, we are now ready to get started. In the project folder, create a new file. I'm calling my file undirectedgraphs.jl, but feel free to name it whatever you like. Let's start by loading graphs, graph recipes, and plots. In this section, we're going to create a very simple graph with 3 nodes and 2 edges. The circles are the nodes, and the lines are the edges. Maybe that's you at node 1, and maybe that's your best friend from school at node 2, and maybe that's your coworker at node 3. Your best friend and your coworker don't know each other, so the only connection they have is through you. This little social network is an example of an undirected graph. There are several different ways that you can construct an undirected graph using the graphs.jl package. The easiest way is to use the graph constructor. The first argument is the number of nodes, and the second argument is the number of edges. The graphs.jl package will automatically generate an undirected graph for you. Now, a quote-unquote graph in the graphs.jl package is just a set of relationships. The graphs.jl package provides all of the basic building blocks for you to construct your own graphs. In addition, the graphs.jl package provides a lot of sophisticated analytical tools for you to analyze your graphs. But the graphs.jl package is not a plotting package. So if you want to see your graph, you need to use an external plotting package. There are several different plotting packages available in the Julia ecosystem. I've provided a link to this page in the description below. The plotting package that I will be using today is called graphrecipes.jl, which is part of the plots.jl ecosystem. Graphrecipes.jl was created by Tom Brayloff, who is also the creator of the plots.jl package. The graphrecipes.jl package has a plotting function named graphplot, which you can use to generate a visualization of your graph. An image of your graph should appear in the plots panel in VS Code. This is what the default image looks like. The 3 nodes are represented by the blue hexagons, and the 2 edges are represented by the black curved lines. If you want to change the appearance of your graph, there are lots of available attributes that you can play with. If you want to label the edges, you need to place the labels inside of a dictionary. For the key value pair, the key is a tuple containing the nodes connected by the edge, and the value is the edge number. Let's say that the edge connecting you to your best friend is edge number 1, and the edge connecting you to your coworker is edge number 2. Now, because we'll be using the graphplot function a lot, let's create a custom function that contains all of the attributes that we want to use for our graphs. The names attribute will display the number of the node. The NV function will return the number of vertices, or nodes, in your graph. The edge label attribute will display the edge labels from your dictionary. The curves attribute will take a boolean for whether or not you want the edges to be straight or curved. By default, the edges are curved. So if you want straight edges, be sure to flip this attribute to false. Otherwise, all of the other attributes are similar to the attributes used in the plots.jl package. Most of these attributes are optional, so feel free to adjust them until you get a look that works for you. Let's take a look at what our graph looks like with all of these attributes. So this image may or may not be what you were expecting. Unlike regular plots, graphs are not necessarily bound by the Cartesian coordinate system. Graphs show relationships in relative space, so the layout is not always predictable. Now, one of the issues with using the automatic constructor for graphs is that the relationships are generated randomly. So if you rerun the graph constructor, you may end up with a relationship that you didn't intend. As you can see in this example, node 3 is in the middle, and it's not showing the correct relationships. A better way to construct graphs is to do it manually. It does take a little more work, but you'll get exactly what you want. To do this manually, let's start by initializing an empty graph. To add a node, or vertex, use the addVerticesBang function. I'm using the term nodes and vertices interchangeably. Hopefully, that won't be too confusing. This will add 3 nodes to the empty graph G2. To add an edge, you can use the addEdgeBang function. When using this function, you need to provide the 2 nodes that you want to connect with an edge. In this case, this will add an edge connecting you and your best friend, or node 1 and node 2. To view your work in progress, you can use our custom view graph function at any time. As you can see, there are 3 nodes, but at the moment only node 1 and node 2 are connected. To connect node 1 and node 3, you need to add another edge. So now we have our completed graph showing the exact relationships that we intended. You can save your graph data by using the SaveGraph function. The LGZ file extension stands for Lightgrass, reflecting the original name of the package. This file will be saved to your project directory. If you open up this file, you can see that it's just a text file containing information about your graph. Specifically, this graph has 3 nodes and 2 edges. That U means that this graph is an undirected graph. Lines 2 and 3 mean that there's an edge between nodes 1 and 2, and another edge between nodes 1 and 3. If you're so inclined, you can actually construct graphs in VS Code, simply by using this file as a template, and then saving your file using the LGZ file extension. You can load this file from disk by using the loadGraph function. And then you can display the graph. If you prefer to save the graph as an image file, you can save it as an SVG file by using the Plots panel. Like any SVG file, you can use a browser to view the image. So those are the basics of constructing undirected graphs. Now let's take a look at how to construct directed graphs. Close out of your Julia session, but keep your file open. Also, clear the graphs from the Plots panel, but keep the panel open. Start a new Julia session by using Alt-J, then Alt-O. Change the present working directory to your project folder. Enter the package manager and then activate your project folder. Exit the package manager by hitting backspace. Create a new file so we can take a look at directed graphs. I'm calling my file directedgraphs.jl, but feel free to name it whatever you like. Let's start by loading the same 3 packages. Like before, we're going to create a simple graph with 3 nodes and 2 edges. But this time, there will be an arrow pointing from node 1 to node 3, and another arrow pointing from node 2 to node 3. Perhaps this is a manufacturing process where nodes 1 and 2 are components that are assembled into a finished product at node 3. This little workflow is an example of a directed graph. Unlike the edges in undirected graphs, the edges in directed graphs are arrows pointing from a source node to a destination node. Just like with undirected graphs, you can use the graphs.jl package to construct directed graphs either automatically or manually. For the automatic constructor, simply use the dieGraph constructor using the number of nodes and the number of edges as your arguments. The graphs.jl package will automatically generate a directed graph for you. Like before, if you want to view your graph, you need to use an external plotting package, like graphrecipes.jl. Let's start by setting up the edge labels as a dictionary. We can reuse our custom viewGraph function from the undirected graph file, so we can simply copy and paste that code. Now, all we need to do is call the viewGraph function to see our directed graph. So this graph is not what we intended. Because this graph was generated automatically, the results may not be predictable. Like with the undirected graphs, a better way to construct directed graphs is to do it manually. Let's start by initializing an empty directed graph by using the dieGraph constructor. We can add 3 vertices, or nodes, by using the addVertices bang function. We can add edges by using the addEdgeBang function. This will add 1 arrow pointing from node 1 to node 3, and another arrow pointing from node 2 to node 3. To view our graph, we can call the viewGraph function again. Perfect! Just like we intended. If you like, you can add arrows in both directions. Each direction is another edge. This will add an arrow pointing from node 3 to node 2. That doesn't look very nice, so let's remove that last edge. You can remove an edge by using the removeEdgeBang function. Okay, that's better. Let's save this graph to disk by using the saveGraph function. If you open the LGZ file, you can see similar information as before. Note the D in line 1. meaning that this is a directed graph, as opposed to an undirected graph. Like before, we can load this file from disk and view it again by using the loadGraph function. If you prefer, you can save the image as an SVG file by using the Plots panel. So now you know how to construct both an undirected graph and a directed graph, which are the two major types of graphs covered in graph theory. Another type of graph is called a weighted graph that may be used to solve some very interesting problems. Let's take a look at how to construct a weighted graph next. Close out of your Julia session and close your open files. Also, clear the Plots panel and close that panel as well. Start a new Julia session by using Alt-J, then Alt-O. Change the present working directory to your project folder. Enter the package manager, and then activate your project folder. Exit the package manager by hitting backspace. Create a new file so we can take a look at weighted graphs. I'm calling my file weightedgraphs.jl, but feel free to name it whatever you like. For this example, I'm going to dock my REPL next to my editor. Let's start by loading a new package called Simple Weighted Graphs, in addition to the 3 other packages that we used before. The Simple Weighted Graphs.jl package is part of the Graphs.jl ecosystem. A simple weighted graph is a graph that allows you to store quote-unquote weight values for your edges. You can think of these weights as representing the relative value or importance of that connection. Depending on the problem that you're trying to solve, you may be looking for high values, or you may be looking for low values. The point is that the edges in your graph may or may not contain the same weight values, and these values may or may not be predictable. For this example, we're going to model a world with 9 nodes connected in a grid. You can think of this as a city grid, where the nodes represent intersections and the edges represent streets. The traffic conditions on each street are different, so they contain different weight values. Our objective is to get from node 1 to node 9 in the shortest possible path, given all of the different weights. Since randomness is involved, I'm going to use a random seed so I can reproduce my results. Using a random seed is optional. When constructing a simple weighted graph, you can use separate vectors to identify the source nodes and the destination nodes. In this example, node 1 is connected to node 2, so 1 would be included in the source vector, and 2 would be included in the destination vector. In addition, node 1 is also connected to node 4, so 1 would be included again in the source vector, and 4 would be included in the destination vector. You can repeat this process until you've included all of the connections. There are a total of 12 connections, 6 vertical connections, and 6 horizontal connections, so your vector should contain 12 elements each. For this graph, the direction of the connection doesn't matter. What matters is that you include all 12 connections. Now that we have our sources and destinations identified, we can use a random number for the weight values of the edges. For simplicity, I'm rounding the values of these random numbers. As you can see, it's just a vector of 12 random numbers, with values ranging from 0 to 1. Now that we've identified the sources, destinations, and weights, we can construct our simple weighted graph by using the simple weighted graph constructor. Sources, destinations, and weights are the 3 arguments. And that's it. Our simple weighted graph has been constructed. But what does it look like? Just like in the previous 2 examples, the hardest part of working with graphs isn't constructing them. Ironically, the hardest part of working with graphs is visualizing them. Displaying the weight values along the edges in the graph will take some extra work. Recall that the edge labels need to be in the form of a dictionary. As before, the key will be a tuple containing the source and destination pair. But rather than mapping to an integer containing an edge number, we need to map the value of the random weight. We can create a function that will loop over the sources, destinations, and weights vectors to construct this dictionary. Now, all we need to do is call this function to construct our dictionary. As you can see, we now have a dictionary mapping the edges to the random weights. Now, we can get working on our plotting recipe. Let's start by setting a default color for our nodes. Next, we need to create our viewGraph function. Conceptually, it's the same thing that we did before, but there are a few differences, so we can't just copy and paste this code. Most of these attributes are optional, so you can play around with these settings until you get a look that suits your needs. One of the big differences is that I added an attribute for the marker color, so we can change the color of the nodes. All of my code is available in my GitHub repository. Okay, let's take a look at what we have so far. So this graph may not look exactly the same as my initial sketch, but all of the relationships are correct. We have node 1 at one corner, and we have node 9 at the opposite corner. There are several different paths that will get you from node 1 to node 9. Each edge contains a different weight, so we need to pick the path that will minimize the total cost of traveling from node 1 to node 9. These weights may represent different things. Perhaps the weight represents distance, or perhaps the weight represents time. You get the idea. This graph is an abstraction of a real-world situation, so we can use it to create simulations. The nice thing about the graphs.jl package is that it comes included with a lot of tools to analyze graphs. One of those analytic tools is called Dijkstra Shortest Paths, which will figure out the shortest path in our graph for us. Dijkstra's algorithm is named after Edsger Dijkstra, who was a Turing Award-winning Dutch computer scientist. He invented this algorithm in 1956 and published it 3 years later. According to Wikipedia, Dijkstra's algorithm is an algorithm for finding the shortest paths between nodes in a weighted graph, for example, road networks. So this algorithm sounds perfect for solving our problem. By using Dijkstra's algorithm, along with a graphs.jl function named enumerate paths, we can find the set of nodes that will get us from node 1 to node 9 in the shortest path. If you look in the REPL, you'll see a vector containing the nodes that we should follow. 1 to 4, to 7, to 8, to 9. Going back to our graph, it would be nice if we could see that path on the graph. We can use a comprehension to create a vector that will change the colors of the nodes along the path to red. If you look in the REPL, you can see a vector containing the color red for nodes 1, 4, 7, 8, and 9, which are the nodes for the shortest path. Now that we have updated colors, we can call the viewGraph function again. The orientation of our graph has changed, but the relationships are the same. And now, the shortest path is easy to see. 1 to 4, to 7, to 8, to 9. Pretty cool, right?
Wow.
So now, we have all the pieces that we need to build a simulation model. To do that, all we need to do is copy and paste some code, and then wrap it inside of a function. The only difference is that I added a line to show the path in the REPL, so we can refer to it if necessary. If you didn't catch all of that copying and pasting, don't worry. You can find all of my code in my GitHub repository. Now, we can just call this function anytime we want to run a simulation. Cool, right? I'm going to use Control-Enter to run the simulation multiple times. As you can see, every time I run it, the weights are different. So the shortest path is slightly different every time, depending on the weights. Now, this is an interesting scenario. If you look in the REPL, you can see that the path goes from 1 to 2 to 3 to 6 to 5 to 8 to 9, which seems like a very long path. Going back to the graph, this is a case where it would have been helpful if I had taken the time to color the edges in addition to the nodes. In any event, you can see that everything is fine going from node 1 to node 6. But at node 6, something interesting is happening. Based on these weights, going directly from node 6 to node 9 would cost 0.7. But going the long way around from node 6 to node 5 to node 8 and then to node 9 would only cost 0.57. So even though it may appear counterintuitive, it does make sense to go the long way around. Pretty cool, right? As before, you can save any of these plots as an SVG file by using the Plots panel. We covered a lot of material today, so let's stop here and recap what we just learned. So, what just happened? Today, we learned that a graph is very different from a plot, and that graph theory can trace its roots back to Leonhard Euler in the 1700s. we learned that the graphs.jl package is the gateway into the world of graph theory in the Julia ecosystem. We learned that we can use the graphs.jl package to construct both undirected graphs and directed graphs. We learned that we can use the graphrecipes.jl package along with the plots.jl package to visualize graphs. We learned that we can use the simple weighted graphs.jl package to create a weighted graph that can be converted into a practical simulation model. By creating this simulation model, we learned that graphs can be deceptively simple and yet surprisingly sophisticated at the same time. If you enjoyed using these packages, please consider going to the GitHub pages for graphs.jl, graphrecipes.jl, and simpleweightedgraphs.jl, and leaving each of them a star. If you made it this far, congratulations! If you enjoyed this video, and you feel like you learned something new, then please consider smashing that like button, leaving a comment, sharing this video, and subscribing to this channel. If you'd like to support the educational work that I'm doing, then please consider using the Super Thanks button. For ongoing support, please consider joining and becoming a channel member. Channel members get ad-free early access to all of my new videos. Thanks for watching, and good luck on your Julia journey.